Good afternoon, and thank you for attending our talk, Odd Perfect Numbers, a Computational Sandbox. This is a joint work between myself, Dr. Michelle DeDeo, and my grad student Matthew Thomas at the University of North Florida. Many algorithmic approaches to finding odd perfect numbers have been attempted, and here we present a novel open-access computational sandbox to search for odd perfect numbers. This is for the purpose of making observations that could lead to new ways to search for odd perfect numbers and their properties. The development environment used, based on Object Pascal, allows for easy modification even by novice coders, and opens up the possibility for cross-platform support for Windows, Macs, Linux, and even mobile platforms. In addition, we'll discuss some of the most current restrictions on OPNs, the current computational schemes used by others, and have a tutorial on how to use the computational sandbox. So what are perfect numbers? If we define sigma of n to be the sum of the divisors of n, then a number is considered perfect if sigma of n is 2n. The most famous example, or the one most used, is for 6, as sigma of 6 is 1 plus 2 plus 3 plus 6 is 12, which is 2 times 6. The abundancy number of any number is the ratio sigma of n over n, so the abundancy number of any perfect number has to be 2. We'll be exploring this ratio in depth further on. As early as Euclid's Elements, Euclid proved a formulation rule, so 2 millennia ago, where q times q plus 1 over 2 is an even perfect number whenever q is the form 2 to the p minus 1, where p is prime. We now call this a Mersenne prime. Euler, in the 1600s, proved that all even perfect numbers are of this form, and we now refer to it as the Euclid-Euler formula. Some interesting facts. Not only is it unknown whether any odd perfect numbers exist, it's not known whether there are infinitely many even perfect numbers. The first few perfect numbers, which are obviously even, are 6, 28, 496, and 8128, and is sequence number 396 in the OEIS. And if you have not visited the OEIS, I highly recommend it. It's an amazing place to play with sequences. All perfect numbers are also known as Einstein-Orr's harmonic numbers. It has been conjectured as well that there are no odd or harmonic numbers other than 1. So if we prove that there are no odd harmonic numbers, that proves that there is no odd perfect numbers, since an odd perfect number would have or harmonic number 2. Well, in 1888, Sylvester proved that an OPN must have at least 3 factors. He subsequently proved that it must have at least 4 and then 5 factors. And if we let little omega of n be the number of distinct prime factors of n, and capital omega of n be the total number of factors including multiplicity, then letting n be of the form p to the alpha times a product of perfect squared odd prime powers, so q1, q2 through qk to even powers, then this must be the form of an odd perfect. And Euler proved that the first prime, which is referred to as the special prime, must be the form 1 mod 4, and its power must also be of the form 1 mod 4. In the 1950s, Touchard proved that n must be the form or 36k plus 9. And if we combine some of the restrictions, we actually get some more modular restrictions on the form of n. Given n equals our form from before, we know that n is not divisible by all 3 of 3, 5, and 7, that the largest prime factor is not only greater than 10 to the 8th, but has been proved that it has to be greater than 10 to the 62nd, and the number of distinct prime factors must be greater than 9, and greater than 12 if n is of the form 36k plus 9. In addition, the total number of factors must exceed 101, including multiplicity. If odd perfects exist, then n itself must be greater than 10 to the 1500, and that's being improved or may have been improved to 10 to the 2000. The second and third largest primes are greater than 10,000 and 100 respectively. The largest prime factor of n has to be less than this cube root of 3n, and n has to be less than 2 to a very large power. So previous algorithmic searches, well, in 2009, Nielsen implemented an algorithm in Mathematica that was different than other approaches to confirm that n has at least 9 distinct prime factors. He fixed the bound b and did not let a bound increase with the algorithm. And this is a great approach. He combined that with using a lemma by Cohen, which allowed for stronger bounds on intervals for primes. And lastly, he compiled a list of 11 contradictions, 4 of which were different than contradictions that were previously used in these algorithmic approaches. Occam and Rao and others have used several methods that navigate what they call roadblocks. They uncover issues while trying to prove a lower bound for n. So they follow an approach of Brent et al. With a method to bypass roadblocks. And with a minor modification of these techniques and factorization methods, they show that n must have at least 101 factors and a component greater than 10 to the 62nd. So our sandbox, as I mentioned before, was created in Pascal. It's in the Delphi environment. Many computer languages have built-in integer data types that are limited to maximum precision, which is far too small to work with numbers as large as 10 to the 1500. The source code for our project is available on GitHub under github.com/mathprojects. We'll talk about that in a moment. And in order to examine the values of sigma of n over n decimal form, you need to consider the floating point number for extremely large precision. So to address these difficulties, we created a software tool that takes numbers already factored into primes and displays a grid of properties that can be exported and analyzed. The software is named OPN Sandbox, and the compiled executables for Windows are available on the GitHub. And in preparation for the OPN Sandbox, the prime powers we want to use for input need to be generated either by Excel, MATLAB, or any other appropriate tool. And then those numbers should be saved as a CSV file, where each row of the input file represents the prime factors and their power, where their number has the form as we've presented. Given the form of an odd perfect number, an example of an input row would be 5, where 5 is p to the 5th power, 3 would be the first q value, 1 would be the beta, so this would really be 3 squared, 13, 1 would be 13 squared, on down the line. So this is the form of an input row, and here would be our n value. This particular example has 10 distinct prime factors, but the OPN Sandbox can accept more with no fixed limit. The number of rows, so we can have multiple rows that we input, is only limited by the available memory, since OPN Sandbox loads the entire file into memory. So here's what our version 1.0 sandbox look like. We have the form of n, so you're reminded of n. The value k is the number of q's that you want. So if you want to take a look at the number of factors, you would add 1 because this is the q's. It does not include the special prime p. You can import via a CSV, and it will auto-populate all of these. Then you would click go, and it would process, and it's going to go through and find certain things. So it will tell you what the bound of p to the alpha is, how large p to the alpha is. It will tell you what the smallest q to the 2 beta is. So here q1 2 to the beta 1, so this term was the smallest q to the 2 beta value. What that value is, bounded by powers of 10, etc. What the largest one is, whether q squared is congruent to certain restrictions, such as 1 mod 16, 1 mod 32. This is in the older version. 1 mod 12, 117 mod 468. This is another restriction that you can easily come up with using modular arithmetic. 81 mod 324 is another one, and whether 105 divides n, that was one of those restrictions we talked about earlier. Now all of that input can be exported into an Excel, and the factors and the properties that we just described are also in that Excel. So this is a great way to kind of get your hands dirty. And so here are more of those conditionals in the header, and notice that the last conditional is that abundancy index of sigma of n over n. And we're going to talk about that more in 1 second. Notice how all these numbers are greater than 2. One consideration in looking at the abundancy ratio is that sigma of n is multiplicative. So that means that we can look at sigma of each of the individual primes as we do our explorations. Two important properties are that for a fixed p-value, if n is greater than m, then the ratio of sigma of p of n over p of n is greater than the ratio of sigma of p of m over p of m. So if n increases, the ratio increases. In addition, if we keep m fixed and we instead increase q, then the relationship is that sigma of q of m over q of m is going to be smaller than the ratio with the smaller prime. Okay, so please keep those in mind. And now I'll turn it over to Matthew. Thanks, Matthew.
This software started out as version 1.0, and so that version is the one that is precisely described in the paper, and it is still currently available. I think even the URL was mentioned in the paper, but if someone were to go to github.com/mathprojects, they can get the binary for that. It would be under binaries, OPN Sandbox, and the version 1.1 has those binaries for Windows only because that was what the state of it was at the time. But the paper mentions that it has the potential of being compiled for Mac and Linux. And so after the paper was submitted, then I started pretty much about the same time I started on version 1.1. If someone were to go to the GitHub page to find the binary for version 1.0, then they may see this README file, which is an extensive write-up of how to use version 1.1, and so they'll know that they can get it for Mac and a command line version also for Windows. Version 1.2 is the current development version. It is not on GitHub, and it is undergoing frequent changes. The changes from version 1 to 1.2 are documented in the source code itself. There have been a lot of changes, and this is the project loaded in the IDE, Delphi. And here is what I will eventually discuss, which is algorithm 1A. And this entire project is available in Dropbox. The idea of OPN Sandbox was about taking some numbers, taking an n that is specified in its prime factorization, and then just tinkering with the numbers and see what there is to see. One of the first things I noticed when I actually started using version 1.2 and using the software as it was originally intended to be used was I noticed that the abundancy was very easy to get to a value over 3. All I did was just keep adding on prime components, and I have a total here of 16, including the special prime. And all of these prime numbers are just consecutive, and it was just very easy to get to a number that was over 3. And so before looking at the abundancy numbers that are closer to 2, I kind of wondered, well, what is it that makes this over 3, and what could I do with these numbers to make it drop below 3, and what might I observe from that? One of the first things I observed was, what I looked for was what was the minimum number of prime components, and within what was the minimum value of the prime factors and the minimum value of their exponents that would get me an abundancy of over 3. So let me just kind of populate just some numbers here in the input. This just gives me some basic input. There's 10 prime components, and let me run this. And when I run this, it will calculate all of these properties for that number in just specified here in its prime factorization. And I was really more focused on this number here. And if I just go ahead and add, I have all the betas set to 1, which makes this not eligible to be an OPN, but I wasn't really looking at that at the time. But as I did earlier, I'm going to add on some prime factors until that abundancy reaches 3. And so we can see that it's a total number of 16 prime components, with 5 and 3 being in there. 7 is skipped, and then the rest of them are consecutive from 11 to 61. So a minimum of 16 prime components with all of their minimum values for the exponents is what is needed for this abundancy to be over 3. Now, if I wanted to see if I can reduce the total number of prime components, what I did was I just changed one of these betas to 2, and I determined that beta 1 is the best one to change. So I change it to 2, and then I'm going to reduce the number of prime components. If I go back to 14 or 15, 14 Qs, then it's still over 3. If I go to 13, it's still over 3, barely. And so if I set this to 12, it will drop below 3. So 13 Qs or 14 prime components is the minimum to have an abundance over 3. And there it is.
Here's some more detailed observations that can be made from the output. This was created by incrementing alpha in P of alpha by 4 and incrementing all the other powers by 1, at least the betas, from one row to the next, and see how the values start fixing for more and more decimal places as those values in the exponents are increased.
Before looking at what makes a number go from abundant to deficient, I was looking to see what it would take to make this number drop below, the abundancy drop below 3. I'm going to add on a few extra prime numbers into n, and I just wanted to get a larger value here for this number, and then show that if we take one of these, I'll take 17, and if I just increment it and watching this abundancy number you may see that it looks like it could drop below 3. If I pick one that's smaller, I should be able to show that there is a number it can be replaced with that causes the abundance to drop below 3. And so I wondered if that was always the case, and that question is open.
Thank you for attending our talk, and I hope you enjoyed this discussion about odd perfect numbers, and that you'll join us in exploring online. Thanks, and have a great weekend.